So what we've got, we're starting Newton's second law today. First and second law. He's got three laws, right, Mr. Newton? Mr. Newton, really smart guy. We'll get more into that as we go along. You're smarter? We'll find out. All right, so to understand how Newton got to his three laws, right, to understand where he got in terms of this stuff, we're going to start at the beginning in our first really scientists, okay, who were thinking about motion and why things acted the way they act, okay? And it helps if I put this in here. Okay. So the first guy who started really thinking about motion and talking about why things moved the way they moved and what was going on, things like that, is a guy named Aristotle. Okay. And Aristotle, he was a Greek philosopher around 4th century BC. So, long time ago, 2,414 years ago, give or take, right? So, this idea of motion and thinking about motion has been going on forever. Forever. You guys don't know that? What, forever? So this idea of trying to explain motion has been around for a long time. Okay? So he came up with the idea. Now again, he's a Greek philosopher. He's not really a scientist. Back then, 400 BC, he's really just hanging out, thinking about what's going on. Right? He's just, again, thinking about what is happening and trying to explain it in things that he knows or what he's observed. All right? So, he believed after watching motion, way things move, things like that, that there's two types of motion. There was natural motion and there was violent motion. The thing to keep in mind first is that when we say violent motion, we don't mean like, two people attacking each other with knives. Okay? They're talking, you'll see what it means, but again, it's not what we think of as violent. All right? So natural motion is what he started with. And the idea of natural motion is that things just tend to move where they would like to go. All right? So they have this natural place that they want to hang out, and that's where they are. Okay? Your pen is in there. All right, so Michaela got in the video. So natural motion just means things like to go up, they like to go down. Right? And it's just naturally where they want to go. Objects have natural resting places that they like to hang out in, and that's that. Right? Boulders, you put them on a hill, they like to go to the bottom of the hill. It's their natural resting place to be at the bottom of the hill. Just is what it is. Right? Smoke, it likes to rise up in the air. It likes to go up because the natural resting place for smoke is going to be up in the air. Seems kind of silly, right? A little odd. But if you think about what they knew back then, 2,400 years ago, they didn't have the technology that we have now, right? They don't have motion detectors or force sensors. They don't have swivels. They don't have anything like that. They just had their eyeballs and their sense of reasoning to try and figure out what and explain what was going on. Right? Does that make sense? Okay. So if you think like they think, essentially if you think like say a 4-year-old, right, for lack of a better term, right? If you have an understanding like a 4-year-old, you see that it probably makes sense, right? Never seen a rock roll up a hill on its own, so it must be that rocks like to roll down the hill because that's where its natural resting place is. Okay? So he comes up with the idea that it's natural for light things to want to go up and heavy things to want to go down. And that's kind of what you see, right? Light things like to travel upwards, and heavy things are always going to travel downwards. Okay. So he takes this kind of natural resting place thing, and he tries to apply it to other things, other instances. And one thing that he comes up with is the earth, right? The earth and how it moves around in the universe and how it moves around in what we know to be the universe. Now, before we had an idea, we had telescopes and we had an idea what was going on, we thought that, this is the earth and everything up in the sky is the heavens, right? And when you look to God, you always looked up. Or you look to the gods, right? You looked up, right? So that was where they hung out. Those were the heavens. Every movie you've ever watched, the gods are always up on top of a mountain, or they're up in the clouds, or they're just up there, right? So they thought that, those are the heavens. And everything that we see, right? Everything that we're watching in the heavens seems to be going around in a circle, right? If I stood there and I watched a star, and I stood there all night long, I would see this the whole way through. It would just go around and around and around and around. Okay? So they kind of felt that, the heavens, they're in natural motion. They just like to go around a circle. There's no starting place, there's no ending place. Okay? What you also see is this idea of planets. It says that, again, they're going around us. So that tells me from my observations that I'm the center of the universe. You guys already knew that, right? I'm the center of the universe? Yeah. Yeah, cool. It's kind of like how most of the kids in the school are. But, so, that's where it gets started, that the earth is the center of everything. Because if you look up and you make the observations of what you see happening above you in the heavens, it seems like the heavens are going around the earth, right? The heavens are circling the earth, and therefore, you must be the center of the universe, okay? That causes big problems down the line, and we'll see that in a little while, but that's where it really gets started. So our natural motion, again, is heavy things like to fall, light things like to rise, and they like to go to this natural resting place, depending on what they are. Violent motion is imposed motion, right? So violent motion is not two people attacking each other with weapons. Violent motion is some sort of object imposing a force on another object, right? It's some object causing another object to move. So they say, a cart pulled by a horse. The horse is imposing the motion on the cart. The horse is making the cart move. A ship in the wind, right? The wind is imposing force on the ship. It's making it move with it. Okay? So do you see the difference? Natural motion, things are kind of moving on their own. It's kind of weird. A little bit of magic is involved, right? But they like to go to their home, kind of like Happy Gilmore. Just go to your home. Okay? Where violent motion, something else is causing it to move. Please tell me you guys have seen Happy Gilmore.
Yeah, don't worry. No.
Great movies. You got good movies.
So Wizard of Oz and Happy Gilmore.
All right, so do you see the difference between the two? One thing seem to be doing it on their own. The other, it's violent motion. One thing is causing another thing to move. Okay? So in violent motion, this movement had an external cause. Right? And it only moved if force was applied. So if you had something in its natural resting place, like a rock at the bottom of a hill, the only way you were going to get it to move was through violent motion. Right? You had to impose movement onto it. You had to apply a force. And if you didn't, it was going to stay in its natural resting place.
Oh my God. That was so low. That's not good.
So let's think about you're hanging out. It's 400 BC, 2,400 years ago. And what's the biggest thing you can think of? Rock. How about one specific rock?
Boulder.
More than a boulder.
Oh.
The absolute biggest thing you can think of. Bigger.
The sun.
Earth, right? The earth itself is the biggest thing you can think of. Right? Because back then, they had no idea about the size of the moon or the sun. They just looked at them. Heck, they could look at the sun and be like, well, when I look at the two, the earth and the moon looks bigger. When they're both up at the same time, the moon looks bigger. We know that's not the case, but that's what they would think, just making an observation.
That's not reasonable, because like, they could be standing far back and see a rock from far away.
But they didn't know that.
That rock's small, and they walk up to it.
But they didn't know that. They're just basing on observation. But I'm standing on the earth, and I can see that the earth is still bigger than the moon, right?
Each moon was different. Each moon phase.
I don't know.
The crescent moon.
I have no idea. I wasn't around back then.
Oh, obvious.
You should make a time
Yeah, you
travel.
definitely.
Yes, I will 3D print a time travel machine, yes. So
Wait, say it Back to the Future.
So
You should totally.
they've got this big, massive thing is the earth, and I'm on the earth now, right? And the awesome thing, or the crazy thing is now, you're sitting there. Do you feel the earth move?
Nope.
No, you don't. So the earth is this big, massive thing, and you don't feel it move. So nothing can make the earth move then. Right? So if we take this idea that nothing can make the earth move, with the other idea previously that everything seems to be circling around the earth, we get the idea that the earth is the center of the universe. Right? And that's what Aristotle comes up with. And while we know now that that's not true, back then it makes sense based on the observations that you were able to make. If you went out tonight and you just made observations about the way things move and you just thought about things, right, just the size of things and what you can experience, you would probably come up with the same conclusion. Right? That the earth is the center, everything seems to be going around. So while it seems silly to us now, back then it wasn't. Right? It was kind of like, oh yeah, well, I can see where you're coming from. You're not right, but I can see where you're coming from. So this idea of the earth being the center of the universe, it goes on for a really long time. We're talking until this guy Copernicus, right? A funny story. When I first started teaching, my first year teaching, this kid saw this name. One kid saw this name. He's like, "Who's Copernicus?" Like, no, it's not Copernicus. It's Copernicus.
Oh,
So
there's no
Copernicus, he was an astronomer, in the 1500s. So we're talking, Aristotle comes up around 400 BC with the idea that the earth is the center of the universe. And he runs with it. Everybody runs with it. For like 1900 years. 1900 years, people are believing that the earth is the center of the universe. Right? Because Aristotle was a very popular, influential guy, and no one had any other way of discounting him. Just, well, that's what we see, so that's what we're going to go with. We don't have the technology or any way of finding out a different reason, so that's what we're going to go with. Copernicus is, again, an astronomer around 1500. This whole idea of the earth is the center of the universe, and you start wrapping in that heavens things, who do you think starts to get involved?
Catholic Church.
The church, right? The church, very good. The church gets really involved, and they say, like, you know what? I like that. And it becomes dogma. It becomes something that everybody believes in if you are a part of that religion. The earth is the center of the universe. Okay? And back then, the church had major control. Major control. They were pretty much the rulers of everything. If you wanted to do something, you had to get their approval. If they didn't like it, you didn't do it, or they made their presence known. So what Copernicus does is he's an astronomer, right? He likes looking at stars. He's got a pretty basic telescope. We're talking the lenses in his telescope are no better than the lenses in your glasses. And he's making observations. And the observations he comes up with they don't work. What he's seeing doesn't agree with what everyone's been taught since the time of Aristotle. They don't jive. Does that make sense? Right? So he's seeing something that doesn't agree with what everyone else has been taught. And he figures that the best way to make his observations agree is if the sun was actually the center of the galaxy. So let's throw out the idea that the earth is the center, that everything revolves around me, and let's now say that the sun is the center, everything revolves around the sun. Now everything agrees with the information, with the data that I've collected. Okay? Because again, you got to remember, Aristotle was just making observations and trying to reason things out. Copernicus is now taking data, collecting information, and trying to then form some sort of theory or hypothesis based on the information that he's gathered. Okay, so there's a little bit of a difference that you see here. The problem is, Copernicus can't really say anything. Copernicus can't be like, hey, this is what I found, and this only works if, because someone's going to go and get him. Right? The church is going to come out and be like, you're wrong, shut up. And if you don't shut up, we're going to, we're going to kill you, more or less. No way to sugarcoat it. Thank you, Michaela. We're going to kill you. Right? So, he works in secret. All right? He doesn't tell anyone. He tells one really close friend. One person that he trusts. It's the only person he tells. Right? And his friend keeps his mouth shut. But eventually, when he finishes his work, Copernicus finishes his work, his friend says, man, you gotta publish this. You gotta write this. People need to know this. Right? At this point, it's around 1543, right? He's getting old. Right? Copernicus is getting old. You see, he dies in 1543. He prints his book May 24th, 1543. Right? Gets out there. Very shortly after, he dies. Old age. No one killed him. So he's dead. Right? He dies. You imagine the churches come banging on the door, coming to get him. They're like, you're going to get rid of this. This is wrong. You're going to go out and you're going to denounce this. You're going to say the devil took you over while he wrote this, things like that. And imagine knocking on the door and going into his house, and there he is dead. Like, well, I guess can't do anything about it now. Can't kill him twice. So what's that? So he knew. What did he know?
He knew he was dying.
Maybe. Maybe he just figured, I'm old enough. I'm old. What are they going to do to an old guy? Right? So years pass. His book's been published. It's popular, but it's kind of like one of those like hidden things where, it's not out there. No one's actually like, reading this out loud, or it's kind of secret. People are reading it like in their bedrooms and they're hiding it under their mattresses and things like that if someone comes home because they don't want to get caught with it, right? His book makes its way down to Rome, to Galileo, right? Galileo, really popular. Guy's one of the first real scientists doing some cool stuff. Back then, the way that rich people flaunted their money today, it's jewelry, it's houses, it's cars, it's all that kind of stuff. If you got a lot of money, that's how you show it off. Back then, the rich families, they would show that they had money by how they'd spend it on art and music and things like that, science. So they'd commission these grand sculptures and these amazing paintings, and they'd fund experiments by scientists, right? And Galileo was funded or sponsored by one of the most influential families of the time, the Medici family, right? They had family members that were high up cardinals in the church. I believe a Medici ended up being a pope, right? They had family members that were high up in government, so they were very, very powerful, had a lot of money. Galileo gets Copernicus's book, right? He reads his book and he says, you know what? You make sense. I like what you say. It agrees with everything that I've done. Because Galileo comes up with one of the first and complex telescopes and learns a lot because of it. And everything that Galileo had observed is supported by what Copernicus writes in his book. Okay. And because of that, he says, he's good. Copernicus is good. I like it. I agree with him. And he gets put on house arrest because of it. Right? They can't kill him because he's too popular. Right? But they put him on house arrest. And while he's on house arrest, he starts doing experiments. Right? He's got nothing else to do. He's stuck in his house forever. So, might as well do some experiments. And a few things that he comes up with this idea of force. Right? He rolls balls up and down ramps, and he makes like pendulums, and they hit each other, and he's the first guy to really come up with like a timer, but it's not a stopwatch, it's actually a bucket that drips water. And he literally would pay someone to count drips. So just be like drip, drip, drip. And like, all right, it took like 3.5 drips for the ball to run down the hill. And that was how they measure time, because they didn't have a stopwatch, they didn't have watches back then. So he came up with this first idea of force, which is any push or pull. Right, so already he's blowing up Aristotle. Right, Aristotle said, things like to roll down the hill because that's where they like to go. It's natural, it's cute, oh, yay. Right? Galileo's ideas of force are more in line with violent motion, correct? Remember, violent motion was an imposed force, something imposing itself on another, right? And this idea of force is much better, right? It's more in line with that part of Aristotle, right? So a force is any push or pull, right? And any object can make that happen. And he looks more into this one specific force called friction. So with friction, he defines it to be a force that acts between materials that touch as they move past each other. So he's saying friction occurs when you've got two materials and you put them on each other and they interact with each other, and that force is created. If you were able to take a really powerful microscope and look down into a surface, like the table surface, you would actually see that the surfaces look like big jagged mountains. Right? They're not smooth like you feel with your hand. Right? There's actually a lot of jaggedness to them. And if you took an object like your bag and you put it down there, these two big mountain ranges, if you think of them that way, these two jagged mountain ranges, they would hook into each other like Velcro, and they would hold on to each other, and they would interact, right? And when they hit each other, that force, right, you'd have one object imposing a force on another. Okay? And friction is just those two surfaces trying to slide across each other in those little microscopic mountain ranges interacting. Obviously, the smaller the mountain ranges, the smaller those bumps are, the less friction is going to be because there's less things grabbing onto each other. The rougher, obviously then, the more they're going to grab onto each other, the greater the friction. If you work in like a kitchen at a restaurant, some floors are kind of rubbery and they have like a sandpaper texture to them, right? You want something like that in that type of environment, because if you're carrying a big pot of like soup or something like that, and you slip, well, one, you don't want to slip, but if you do slip, you don't want to end up with that soup all over you, correct? Or you don't want to slip and end up with your hand in the fryer later, right? French fries and fried fingers, okay? So, that doesn't sound fun? No? Could be a new delicacy. So, that's where we want a lot of friction. Places we don't want a lot of friction, hockey, right? Engines, car engines, you don't want a lot of friction in car engines because friction creates heat. If your engine gets too hot, that's a problem.
You want it in track.
Right?
You run faster.
There you go. So, some places friction's good, some places friction's not so good. Okay? And you need to think about those, what's going on. Friction, though, is very important. Things don't occur without friction, right? You can't walk without friction. You can't put on clothes without friction, right? You couldn't write without friction because the pen wouldn't be able to, roll the ball that's in your pen, right? And then to move the ink wouldn't stick to the paper, right? All those things wouldn't occur because there's no friction. Right? So sometimes friction is a nasty beast that you have to deal with. Other times it's massively important. Right? And for the most part, friction is something that you do want. Otherwise, there's not a whole lot you can do. Okay? So again, we talked about it's caused by irregularities in the surface, and if there's no friction, an object's going to move forever. Friction is always going to oppose the direction of motion. So an object moves to the left, friction is going to go to the right. Okay? So if there's no opposition, an object's going to continue to move forever and ever and ever and ever and ever and ever and ever and ever. Okay. Good. Okay. So if we have friction, a force is needed to keep that object moving, right? Because friction's opposing you, so you need something that balances that out or counteracts it. So we can see right there that friction, one is a force, but it acts, like a vector. So you can add or subtract it, but the direction is very important. Right? So force, it is a vector. Right? So a force, if you've got friction acting on you again, you need to apply a force in a direction that opposes it if you want that object to move. Okay? Again, friction is going to cause an object to slow down. Another item that he came up with and he looked at was inertia. I want you to think, don't say it out loud, I want you to think of an object that is hard to move. Think of an object that is hard to move. Max, what do you think? What's an object hard to move? Tree. All right. Rita, what do you think? Hard to move object? A car. All right. Isabella, what do you think? Hard to move object? A house. What do these three objects have in common? They're heavy, right? If they're heavy, what do you typically say they have a lot of? Mass. Right, they're good. They have a lot of mass. Okay. Now how about an object that's easy to move? Can you come up with an object that's easy to move? A ball? Okay. Oh, chair? A leaf? All right. Depends on the amount of water.
It's like a puddle.
A puddle, okay, a puddle. All right. What do these things all have in common? What do all these light things have in common? Oh, they're easy to move. They're all light. They have a low mass, right? They have a low mass. So inertia has to do with the mass of an object. The more mass you have, the greater amount of inertia you have. That means it's hard to change your motion. Right? You think of a car, you're trying to push a car, it's really hard to change its motion. If it's at rest, it wants to stay at rest, right? It wants to stay doing nothing. And it's really hard to get it to go, right? It takes a lot of force to change that from stopped, resting, to actually moving and doing something, okay? So inertia has to do with changing that motion, whether it's getting it going, slowing it down, or changing its direction, right? If you're getting chased by an elephant, because that happens quite often, right? Has it occurred to you before, Isabella? Yes, you've had an elephant chase you before? So if an elephant chases you, the best way to get away from it is to run in zigzags. Because it's very hard for an elephant to change its direction because it has a large inertia.
Wouldn't you just keep running for
Yeah,
it?
I mean,
Yeah,
the
just
elephant
keep
could
running
probably
for it.
figure it out.
But I don't know
It's not
if
quick enough to, by the time you're like,
but it just wants to, but that's what you're thinking because we're smart. Elephants are smart, but I doubt they have the ability to be like, oh well, if I just run straight and he zigzags, I'll eventually catch up to him.
Yeah, but the displacement, yeah, the elephant will be running straight and you're zigzagging, taking time, and then he hit you in the middle.
You're just gonna get trampled either way in this situation.
So-
Take a 90
He's just gonna come running at you, right? And he's gonna try and run at you no matter what. Because he's got a huge amount of inertia, it's very hard for him to turn and change the direction he's traveling in because everything wants to just continue to go that way,
Oh, I get what you're saying.
right? So think about if you're pushing a shopping cart, you go to Mark Basket, you just get the shopping cart, there's nothing in it. It's very easy to maneuver wherever you want to go, right? But as you put everything in there, and you push it, and then you try and turn it, you're like,
That's where you
it's really hard to get it to move, right? Get it really hard to turn it around that aisle.
The back tire.
Oh, lift it up, yeah, wheel it around, right? Same thing with the elephant. The elephant is like that loaded cart. He just wants to continue going straight. It's really hard to get him to move. All right, that's what inertia is. It's the ability to change its motion. We see a shift now. Aristotle wants to know why. He tries to make those explanations based on what he sees. Galileo and Copernicus, they want to now talk about the hows, right? They're trying to interpret their data. They want to know, how does it move? Make those predictions as opposed to why does it move? So the last thing, we'll leave it here, but here's an interesting thing. Galileo ends up dying, natural causes, right? In his house, I think. Yeah, suspicious. He dies, I forget the year, I want to say it's like 1642, right? He dies on Christmas Day in like 1642, something like that, right? So, but here's the interesting thing. Isaac Newton is born the same day.
When one door closes, another one opens.
Yes. There we go, right. It's meant to be. So the day that Galileo dies, Isaac Newton is born. And Isaac Newton just blows everything up.
At one point, I accidentally got in it.